All right, let's. Okay, so let's see today. Let's see. Well, first, let's go back to Moodle. Well, we want to do the chapter 5 problem set. And then we can carry on with chapter 11. All right, so first let's go get Moodle. All right, so the chapter 5 problem set, wow, this is a long list, isn't it? It's way down here somewhere. There it is. Okay, so this is all trigonometry. Now, with the questions like these, what you might want to think about doing is having that unit circle open in front of you. And so let me go get that open. That would have been, of course, chapter 5. Of course, there are also charts in here too, but I think the unit circle is the way to go because it has a lot of combinations here that are going to be very useful. So let's go get that chart. There we go. So not that every single one of them is on here, but a large number of them are. And if not, hello, you might be able to find it on your calculator. Now, let me get this one out for a second. I seem to remember last time we went over this, the iPhone calculator, at least, does have some rudimentary trig functions on it. I think it's geared towards degrees rather than radians, which is probably better. Hold on. I'm looking for mine. All right, so you turn it on its side. And yes, in the bottom left-hand corner, there are some trig functions. Now, the only issue here is that, let's say you do go for the sine of 60 degrees. You type 60 sine. Now, here's the awkward part. The calculator is not going to give you this radical 3/2. It's going to come back 0.866 something, and that's fine. But, you just have to recognize that whatever this number is, it's most likely the result of some kind of a radical divided by another whole number. And you can figure it out if you want to, but if you do put down 0.866 as the sine of 60, that's fine. But I would say that for the most part, you can do these with your unit circle. So just remember the way it works is that for each pair, hold on a second. I'm looking for my pen here. Hold on. All right, I found it. All right, so anyway, yes. So the way this works is that for each of these ordered pairs, what you're actually seeing here is that the first term, oh, wait a minute, I have to set up my tablet. Hold on one second. Okay. All right, all set. So we have, yes, as I started to say, for each of these ordered pairs, what's actually happening, if you remember from last time, is that the first term is the cosine. And the second term is the sine. Right? So now it should say that here, but it doesn't. But remember, this is how they were defined. We went through the derivations last time. So just remember, for each of these, the cosine is the first term and the sine is the second term. If you're not sure, you can go back to your calculator and use this as an example. Ask for the cosine of 60 degrees, and it should come back 1/2. And then you'll know for sure that the first term is in fact the cosine. So cosine 60 on your calculator does come back 0.5. Right, perfect. All right, so let's get to these. So we'll look at the calculations. And let me just save this for a second. So we'll start with 3/4 radians. Now here, all you're being asked to do is calculate the angle in in degrees. So how does that work? So there's another chart in here that will help us with this. There's a conversion table. I know there is. Let's see if we can find it. And once we have that table in front of us, this should be, oh, here it is. All right, and again, this doesn't cover every single one of them, of course. But you should have no trouble figuring out once you see this chart. So for example, we're looking for 3/4 radians. According to this chart, 1/4 radian is 45 degrees. So basically that means you'll just multiply this by 3. Okay, so in other words, this equals, or you could write it in a few different ways, but what you really should do is what equals 3 times pi over 4 radians, because we know what that is already. Okay, so pi over 4 is 45 degrees. So that's 135 degrees. Now, there's another way of doing this, which might be a little bit quicker and doesn't really depend on there being a chart. Another option you have is to do this. Just take the original expression and multiply it by 180. That actually might be a little bit quicker. Because if you multiply this out, 180 times 3/4 is 135 degrees, okay? So you can look up, predefined values in a chart and then adjust them or figure out the multiples of them. But a quicker way might be to simply just, in each case, multiply what you've got by 180. And then that will convert these into degrees. So for this one, for example, pi over 9 radians is the same thing as 180 times pi over 9 degrees. It's that 180 that's converting it, and therefore you end up with 20 degrees. Okay, so the radians are converted into degrees with the constant 180, which is very simple. Now, what happens with these negative ones? Well, with the negative ones, we have to be careful because remember, that means you're going around the unit circle. Let's see what happened to my unit circle. With the circle, yeah, if you're going around, let's say in this diagram, you're going around the circle counterclockwise. Those are the positive angles, if you recall. Going around the other direction, clockwise, is what we mean by negative degrees. Okay, now what you can do is if you have a negative degree, you can convert it into the equivalent positive degree. So let's do that right now. Okay, let me go get the unit circle. There it is. So what are we faced with here? We've got negative 5/4 pi radians. So if you look at the circle, let's see. Oh, this one doesn't have radians. I thought I had another. Oh, wait. Yes, it does. They're right here. But it doesn't have the negatives. That's the thing. So here's what we have to do. We multiply this by 100. And 80, I mean, 180. We're going to get a negative number, which is fine. But if we need the positive degree, here's what we're going to do. So if you multiply that out, you're going to get minus 225 degrees, which is right. I mean, that's the correct answer. But if you are interested in the positive angle, what you have to do is just visualize what's happening here. So to get to the 225, you're going clockwise. So you're going 180 degrees to get through the fourth and third quadrants. And then here, this divides the quadrant in half. This is a 45-degree angle. And so this represents minus 225 degrees. So the question is, how far do you have to go in the counterclockwise direction to reach the same point? Well, to get through the first quadrant, you have to go through 90 degrees. And then the second quadrant, this is also 45 degrees. So that means you've got 90 plus 45. And so negative 225 degrees is the same thing as positive 135 degrees. Either one of these will give you the correct answer. Now, if you forget how this works, there's a simple rule of thumb here. And by the way, you might recall in the chapter, we refer to these as coterminal degrees, angles. These are coterminal angles because they have the same, it's the same terminal point. In other words, they bring us to the same location. And if you notice, the absolute value, the sum of the absolute values is 360 degrees. In other words, the absolute value of negative 225 and the absolute value of 135 does in fact give us back 360. So that's how you know you've done this correctly. If the absolute values add up to 360, that means you have correctly identified the so-called coterminal angles. So when one is negative, we can easily convert it into the equivalent positive angle through this procedure. Now, like I said, though, there's nothing wrong with saying negative 225, but I think it's easier to visualize by referring to it as 135. So therefore, either one of these is correct. All right, and then finally, what do we have here? Oh, pi over 3, very simple one, because all you have to do, like I said, is multiply this by 180. And this one we can do in our heads. This is 60 degrees, obviously. All right. So, and of course, anytime if you want, you can double check this on our unit circle. This is pi over 3 radians, which we find right here. What do you know? We looked at this already today. So the chart is telling us that pi over 3 is equivalent to 60 degrees. And so that's just what we determined. But now we remember why. Why is that the same? Because if you multiply the pi over 3 by 180. Yes. Okay. So anyway, for each of the following, convert the angle to, okay, well, now we're going the other way around. We're going to radians. So here's what you need to do. Take the 90 and in these cases, divide by 180. Okay, so in other words, 90 degrees. If we divide that by 180, all right, well, we don't need that symbol every time, all right. 180, and then you have to multiply by pi. Don't forget the pi. And that equals 1/2 pi radians, or pi over 2. All right, and you can confirm that with our unit circle diagram. Go back to 90. And yes, there it's right there. 90 and pi over 2 mean the same thing. All right. Well, now, what about 180? Well, 180 should be very simple then, because if you're going to divide that by 180, I think we're all set. It's just pi radians. So that's how it's defined. 180 right here and pi mean the same thing. Now with this one, we could leave it as negative, but I really think it's a bad idea. Let's do this. Let's remind ourselves what negative 90 actually means. So remember, with negative degrees, you're going clockwise. In order to reach that on this side, you're actually going 270 degrees. So I think in a case like this, your best bet is to convert this into positive 270 because they mean the same thing, of course. And then you do the conversion into radians. Okay, so in other words, this equals positive 270 degrees. And then you can work on that. Okay, 270 times 1, or divided by, sorry, it's divided by times pi results in 3 pi over 2 radians, or 1.5 radians. All right, and then finally for D, this is not a problem because it's already positive. So let's just go ahead and apply this technique. And in fact, you'll see that we've already determined, because we understand how these things work, that the answers to C and D have to be the same because they're the same angle. Okay, so in other words, negative 90 and positive 270 are coterminal, meaning they're the same angle, only one is positive and one is negative. So the answers to C and D have to be the same. Very good. Now, what about these? Now here we're looking for the actual values. We're not doing any converting. We're just saying, what's the value of these? And of course, if you're finding these on the unit circle, they're all going to be written in terms of radicals. If you do it on your calculator, you'll get decimals, and that's fine. But maybe we can do it both ways. So why don't we look at this one? So if you look at the unit circle, pi over 6 is way over here. This is 30 degrees. And so you can see that given that the first term here is the cosine and the second term is the sine, then the sine of pi over 6 is a half. All right, so just remember, when you're looking at these ordered pairs, the cosine comes first and the sine comes second. If you go to your calculator in this case, of course, it'll do the same thing. It'll just give you 0.5. All right, but then what about sine of pi over 3? All right, let's look at the unit circle. Oh, by the way, I just remembered, this is, if you're going to use your calculator, the calculator does have a radian button. I'll tell you what, why don't we do this? Let's before we go any further, let's see how this would work in your calculator. Because it's in radians, there's an extra step involved. You can actually manually convert pi over 6 into 30 degrees if you want to, but this might be a little quicker. There's a button in the bottom left-hand corner called rad for radian. If you hit, oh, okay. There we go. So hit radians, and now type in, there's a pi button on here somewhere. Where is it? Yeah, there it is. It's in sort of, if you look in the very bottom row, it's not right next to the 0, but it's very close to it. Type pi, and then divide by 6. Oh, that didn't work. Okay. Ooh, all right. So I'll tell you what, that didn't work. So here's what we're going to do. When you start all over again, make sure you're in the radians mode. Hit pi divided by 6, close parentheses. Oh, no, I know what the problem is. Put pi divided by 6 equals, and then hit the sine button. Okay, that's what you have to do. Okay, so I wasn't sure because I haven't really used this calculator, its trig functions before. So in other words, the buttons are radian. This is going to switch you into the radian mode. Then you'll type pi divided by 6 equals, and then you'll hit the sine button. And that will give you a half. Okay, so now here's the thing you've got to watch out for though. Once you're in the radian mode, it's going to stay in the radian mode. So here's what I recommend you do. Be sure to switch back to the degree mode as soon as the problem is finished, because if not, you know what's going to happen. You're going to do a problem and assume that it's in the degree mode, and it's not. So because we don't use radians very often, and by the way, to switch it back, if you notice in the bottom left-hand corner, the rad button, so to speak, is now showing degree or deg. Hit this button to switch back to degree mode. Okay, so when you hit that, now another thing I want to point out, when the calculator is in rad mode, there is a small message on the upper left-hand corner that says rad, just to remind you. When the calculator is in degree mode, there is no message at all. So you've never noticed this before because we never needed it. So in other words, if you switch back and forth between the radians and the degrees, when you're in radians mode, it actually says it in the upper left-hand corner. When you're in the degrees mode, it has nothing at all in the upper left-hand corner, which means that's the one they assume that you'll be in most of the time. And only occasionally you'll use the radian mode. So that's why they go out of their way to put that message up there. So if you see it, you'll say to yourself, oh my God, I'm in radian mode. If that's what you want, that's fine. But if not, it's a little reminder that maybe you'll want to switch back to degree mode. Okay, so this will help us solve for all of these without the unit circle. But these are conversions. These you do need to look at the unit circle for. The first two that we did, converting between degrees and radians, the calculator can't really help you with that. But the unit circle can. When we get to these, where you're actually trying to calculate them, then the calculator can do all of these, as long as you're careful about which mode you're in. Now, having said that, for the more complicated ones, you'll sometimes get these very messy decimals and not the radicals, but that's not really a huge priority. I mean, if you really want the radicals, you can come back here and find them. So like here, sine pi over 3. Now, we can look at the table. Pi over 3, as you can see, is 60 degrees. The sine is radical 3 over 2. Okay, so you can make a note here from the unit circle. This equals, and then you put in there radical 3 over 2. Let me just enter that in here with my trusty equation editor. Okay. All right, where are we? Now, if you were to actually calculate this though, if you go to your calculator, so for using the calculator, you have to first switch to the radian mode. Okay, and once you're in that mode, what you're going to do is just type pi. No, sorry, pi divided by 3. Don't forget the equal sign. And then hit the sign button. And so let's do that. Pi, first radian mode, pi divided by 3 equals sine 0.866. Okay, but if you were to actually go to your calculator now and calculate the square root of 3 divided by 2, you'll see that it is in fact 0.866. In other words, this is the correct answer. It's just that it's not expressed as a radical. Now, here's a helpful hint though. If you're really determined to show the radical, just keep in mind, if you look at this chart, almost without fail, the radical is either 2 or 3. In fact, I don't see any others in this chart that are anything different. So if you really are determined, I must know the correct radical, try 3 and try 2. And most likely that will do the job. All right. Now here's one, cosine pi over 6. Now again, we can just go right to the unit circle. And if we do that, that's radical, oh, what do you know? It's the same, radical 3 over 2. Okay, so from the unit circle, this equals, and it just so happens to be the same thing, radical 3 over 2. Okay, but if you're going to use the calculator, of course, switch to the radian mode. And then it's going to be almost identical, except for the fact that, oh wait, sorry, this is pi over 6, but still, it's a similar setup, pi over 6 equals, and then do the cosine. And there you go, it's the same. All right, and then we have one more here, cosine pi over 3. So again, you can go look it up in the unit circle. Pi over 3 is way up here, 60 degrees, and the cosine is 1/2. Okay. All right, but again, if you want to use the calculator, now why would you want to use the calculator, by the way? What if it's not something even like this? What if it's something bizarre like 8 pi over 9 or something that's not actually on here? Then you really do need the calculator. Okay, so the unit circle is fine as far as it goes, but it only goes up to sixths. What if we need ninths or 12ths or 16ths or something? Then you really do need the calculator. So it's good to know both techniques. Switch to the radian mode. And then you're going to have pi over 3 equals, and then take the cosine. And it should turn out to be 1/2. Okay, so let's do that. Pi divided by 3 oh, make sure in the radian mode, then pi divided by 3 equals, and then do take the cosine, and it's going to be 1/2. All right. Okay, here we go. Now for the next group, oh, reference angles. All right, so what we need to do is remind ourselves what exactly is a reference angle. So the reference angle, let's go back to the slides for a second. It is the smallest acute angle that can be formed from the terminal side and the horizontal axis. So if you're in the first quadrant, the reference angle is your angle. In the second quadrant, it's 180 minus whatever angle you're given. If you're in the third quadrant, it's angle minus 180. And in the fourth quadrant, it's 360 minus angle. So how does that work here? So basically, what I'm going to do is just copy these in here. So remember, now the first quadrant covers the angles from 0 to 90. And when you're in the first quadrant, then the reference angle equals the actual angle that you have. Okay, in the second quadrant, which is 90 to 180. Then what you have to do is say 180 minus the third quadrant, which is from 180 to 270 degrees. The reference angle equals the actual angle minus 180 because it's larger than 180. And then if you're in the fourth quadrant, which is between 270 and 360 degrees, then you're looking at 360 minus the angle. So for part A, 90, your answer is 90. Okay. For part B, you're at 240, which means you're in the third quadrant. And the rule for the third quadrant is actual angle minus 180, which means 240 minus 180 equals 60 degrees. Now, if you're not sure, you can draw a diagram. Let's see. So 240 means you're going through first two quadrants, and let's say you're about here. Let me draw that better. Okay, so this is what they're trying to capture, this piece. The angle with respect to this horizontal axis is in fact 60. Okay, so in other words, yes, you're going all the way around. Actually, let me draw this again. A little bigger so you can actually see what I'm doing. If you're at, let's say here, this entire angle is 240 degrees because going through the first two quadrants is 180. Then we add 60 more degrees to that. So basically, the reference angle is telling us how close are we to the nearest axis. That's really what it's doing. Or you can think of it as the angle that could be formed from the terminal side and the horizontal axis. So I hope that by writing it this way, and then up here would be 180. So they add up to 240, but the reference angle is the angle with respect to the horizontal axis. How much further did I have to go to move into the third quadrant here? That's what we're trying to capture. All right, so then the third one is, negative 170. What do we do with negatives? All right, well, now again, negatives are kind of a nuisance. I think you'll agree. So why don't we do this? Why don't we convert it into the equivalent positive angle? So negative 170 means you're going clockwise, not quite all the way through the fourth quadrant. Now, you can see this little slice is 10 degrees because the total in the fourth quadrant has to be 180. That actually is the final answer. But what I wanted us to see, though, is that to get to this point in a clockwise direction, this would be equivalent. Let's see, wait a minute, negative 170. Yeah, what we're doing here is going all the way around. And that's going to be 190. No, you know what? No, sorry, I drew this completely wrong. Sorry, my fault. No, I messed it up completely. I was thinking of 180. It's 90. All right, try that again. Okay, so in other words, negative 170 is almost all the way into this third quadrant, not the second, the third. All right, so in other words, you're coming around this way. So there's I'm almost, but not quite reaching 180 degrees. And that 10 is in fact the reference angle. You can see it visually just by looking at the diagram. But why don't we do this instead? Just recognize that coming from this direction, this is 190. They both mean the same thing. All right, so 190 degrees and negative 170 are coterminal. And again, if you notice, we can double check that by adding up their absolute values. So what we're going to do then is say, well, listen, with 190, we can go back and use our rules. Okay, so 190 puts us into the third quadrant right here. So therefore, the answer is at actual angle minus 180. So that, in other words, the positive angle minus 180 is 10, and that's the answer. But you can see it in two different ways. First, by using the rule based on the positive angle of 190, but secondly, just looking at the picture. Remember, we're looking for the angle with respect to the horizontal axis, and that would be the 10. Okay, so this 10 degrees is the angle with respect to the horizontal axis. All right, ooh. And then finally for D, we have negative 135. So again, we probably should convert that into the positive version because it just seems easier. Okay, positive numbers are much easier to deal with. So you'll recall, and we already had this example once before, negative 135 means you're coming through the fourth quadrant, and then another 45 degrees. In other words, think of this as 180, 45, and a total of, no, sorry, I messed it up again. This is 90. Much better. Yeah, this is 90. All right, so they added to 135. So this is our negative 135, but it's usually easier to think of this as positive 225. Because you're going 180 degrees through the first two quadrants and then another 45 degrees here. So negative 135 is the same thing as 225. And we know that we're in the third quadrant here. So the rule, the third quadrant, is, let's go copy it, actual minus 180. So if we call our actual 225, instead of negative 135, 225 minus 180 equals 45. And so you can see from the diagram that that must be correct, because what you're actually looking for, in fact, let me color it in for you, is this. That's what we're aiming for, the angle with respect to the horizontal axis. All right, now, unfortunately, we have to do the same thing with radians. I know, nobody likes radians, but that's okay. We'll get used to them. And so, there are rules for the radians, okay? And I'm gonna go get them from the slides. And the rules, of course, perfectly correspond to what we're seeing up here. It's just that they're converted into radians. In fact, you know, let's do this. Let's copy them. And then convert everything into radians. So the first quadrant is everything from 0 to pi over 2 radians. But the rules won't change. Now, the second quadrant is pi over 2 up to pi. And so this 180 is going to be replaced with pi. And now 180 to 270 is everything from pi to 3 over 2 pi radians, that is. And so actual angle minus pi, 180 becomes actual angle minus pi. And then finally here we have everything from 3 pi over 2 radians up to 2 pi radians, that is. All right. And now this becomes 2 pi minus the actual angle. So basically, nothing has changed. And so hold on one second. All right, so let's do what we can. So part A, we have 2 pi. Now in all of these, really all we have to do is identify which quadrant we're in. There's no negatives here, which is kind of nice. So 2 pi, the reference angle, now 2 pi puts us in the 4th quadrant. So that one's just going to be 0. Okay, and remember 2 pi means you've gone around the complete circle. So you're basically right back to the origin. Okay, so let me just quickly sketch that in here. You're just right back where you started from. So the angle is 0. The angle with respect to the horizontal axis is just 0. Okay, now how about the second one, 2 pi over 3? 2 pi over 3 is more than a half, but less than pi radians. So in the second quadrant, so here the rule is pi minus actual angle. Which means pi minus 2/3 of pi and of course, what you're basically doing here is subtracting 2/3 from 1. And so therefore you end up with pi over 3. All right. And then what about C? They're asking us for the reference angle for 5 pi over 6. So 5 pi over 6, again, is between half of pi over 2 and pi. It's in the second quadrant. So it's just like this one. We're just subtracting. All right, so we're going to have equals pi minus 5 pi over 6. And so we're just going to wind up with pi over 6. Beautiful. Well, that was easy. And then the last one is 7 pi over 3. Now this time we're in, let's see, where are we? 7 pi over 3, that's more than 2 pi. So we have to watch it with this one because we've gone all the way around the circle. And somewhere along the way, we noted that this is 2 pi. Oh, wait, yeah, that's right. This is actually 7/3 is actually 2 1/3. So that means you've gone 2 pi plus another third. So this angle is the same as this one. Just like, let's say you had an angle of 450. This equals 90 because 450 minus 360 is 90. And up here, this is because 7 pi over 3 minus 2 pi is pi over 3. So in other words, every time you go around the circle once, you're basically starting all over again. So 7 pi over 3 is the same as pi over 3. It's the same angle. Just like with degrees, 450 is 90 because you're going around the circle once and then another 90. So that being the case, we're actually in the first quadrant. That's the tricky part. So I'm going to copy the rules for the first quadrant. Yeah, so they were all easy up to that point. And then all of a sudden, we found ourselves going past what we're used to seeing. And that means that the reference angle in the first quadrant is just the actual angle, which means pi, not 7 over 3, but pi over 3. Okay. All right. Now, the last batch of these are the other trig functions that we haven't really been addressing. Now, the tangent is on your keyboard, on your phone. So you can do that one directly. All right, so what you can do is a couple of things. First of all, just remember the tangent of theta equals the sine of theta over the cosine of theta. That's one of the identities that we did in here somewhere towards the end, I think. Or maybe towards the beginning. Oh no, here they are. So yeah, a tangent is equivalent. So what you can do here is actually calculate with your calculator these two. Actually, what you could do is go to the unit circle first. The unit circle only shows sines and cosines because all the others are defined in terms of those two functions. We don't really need the others because we can figure them out ourselves. So if you go back to the unit circle, the sine of pi over 6, there we go. So we're looking at pi over 6 or 30 degrees. So according to this, the sine is a half and the cosine is radical 3 over 2. So algebraically, you can rewrite that as 1/2 times the inverse of the denominator, or 2 over radical 3. So you end up with 1 over radical 3, but remember, we typically try to avoid having radicals in the denominator. So what we can do is multiply this by radical 3 over 3, and that's our final answer. Now, if you want to do this in the calculator, of course, you're going to get a number which is not radical 3 over 3, but you're actually going to get the correct answer. Okay, so, you can decide what to do. You can look at the unit circle, but remember, if the unit circle doesn't have what you need, the calculator always works. So you'd calculate, in fact, why don't we do this real fast? So you go to your calculator, and remember, you should be in the radians mode to do this. Don't forget about that little detail. So you'll take pi over 6, and then you'll take the sine. All right, so in radian mode, you'll put pi divided by 6 equals, and then sine. And you'll come up with a half. And the second one, for cosine, pi over 6, and so for that, you're going to get pi over 6 cosine. Now, in the calculator, you're going to end up with 0.866, which you already know is radical 3 over 2. And so to calculate the tangent, substitute these values. And that's going to be approximately 0.577. Now, if you go, now we already know the actual answer is radical 3 over 3. Go to the calculator and type in radical 3 divided by 3, and you'll see that it's almost exactly the same. Okay, so that's a possibility. But since we have the unit, the unit circle, you might want to think about using that. But what you do have to remember is how these functions work. So for example, the secant, as you recall, and if you don't, it's in the slides, is 1 over the cosine. Now the cosine of 6 is right on the unit circle. radical 3 over 2. And then we can rewrite this as 1 times 2 over radical 3. And then we can write this as 2 radical 3 over 3. Okay. So you can now, of course, go ahead and do this on your calculator. Up here, you see, we already know that cosine pi over 6 is 0.866. So if you take 1 divided by 0.866, that's about 1.1547. And if you go to your calculator and do 2 radical 3 over 3, you'll get the same thing. Either way, you're getting the right answer. It's just that here you're writing it as a radical, which actually looks kind of nicer, but either way, you get the same number. Now, by the way, let me remind you where these identities are. Towards the end here, I think, oh, right. Okay, so secant is 1 over cosine, cosecant is 1 over sine, cotangent is 1 over tangent, which implies that it's cosine over sine. And of course, these are all going to come in very handy. Now, cosecant is the inverse of the sine. Now, we just got through calculating earlier the sine of pi over 6 is a half. Well, we got lucky here. And that's just 2. I like it when it turns out nicely like that. All right, and then finally the cotangent, which as you just saw is 1 over the tangent. And up here, we figured out that the tangent is, wow, 0.5774. Or what we could do is just use radical 3 over 3. That's probably what we should do, radical 3 over 3. Now, of course, there we go again. We have a radical 3 in the denominator, which we don't normally like to have. So 3 radical 3, 3 over radical 3 is the same as 3 radical 3. Oh yeah, look at how that turned out. But that is easier, isn't it? Yeah, it's just radical 3. Now, radical 3 is approximately 1.73. And so I do want to point out here, though, that according to the identities we just looked at, we can rewrite this as the cosine of pi over 6 over the sine of pi over 6, because it's the same thing. And so remember, the cosine of pi over 6 turned out to be, oh God, where is it? All right, I know it's here somewhere. Let's look at the unit circle. The cosine of pi over 6 is radical 3 over 2. And the sine of pi over 6 is a half. All right, so this is the equivalent of times 2 over 1, and the 2's cancel out, and there you go. And that's it. All right. Boy, that was a lot, but we're done. No more trig for a while. I think you'll be happy to hear that. We're moving back into something a little bit more down to earth. And that something else is what we call probability theory, which is a very important branch of mathematics. And what's also interesting about it is that it's sort of sometimes it's called discrete math because we do not have continuous values. We have a lot of integers and a lot of scenarios where something is either true or false, that type of thing. So it's a very different type of math. Very useful, very important. So we'll put this aside for now. And we'll get to chapter 11. Now, I think we may have just started to take a peek at it. It doesn't matter. We'll start all over again. But before we do that, there are, like I was saying, I think I mentioned this last time, this topic lends itself very nicely to videos. It's just, there's something about the subject matter that it's just so much easier to turn it into videos. It's kind of hard to turn trigonometry into videos, although I think there actually was one video I wanted to show you about trig, which is about real world applications. And I think you'll find that very interesting. And then when that's done, we're going to start 11. Sequences, counting and probability theory, a very interesting branch of math. And it also forms the foundation for statistics, which we'll have a brief look at as well. So there's a lot of subjects in this chapter, a lot of very interesting and important subjects we're going to look at, but they all have the common focus that they're designed to help us calculate the likelihood of uncertain events taking place. In other words, this gives us an opportunity or a methodology for measuring uncertainty. And of course, in the real world, there's uncertainty everywhere. We constantly need to model what we think is happening in the real world so that we can make predictions about what will happen in the future to help us decide what actions to take. So if you're running a business, for example, you better have a pretty clear idea of what kind of demand there is for your product, and that can be obtained by using probability theory. So, all right, so here's what I'd like to do. Let's go back, before we forget all about our trig, that one video I wanted you to see about applications, we can do that now. And then we can go on completely to probability theory. So we'll start with this one. Real examples. Now this is one of the things that, the reality is trig functions are very, very useful in the real world, especially like I mentioned, trigonometry and engineering and architecture. These very heavily applied fields do depend very heavily on trig functions. So they're going to give us some ideas about what interesting applications can be implemented using trig functions. So first, let me send you the video, the link to the video, that is, and then let's check it out. Oops. All right, there it is. All right, let's check this out.
Fences have finally worn out their welcome. Why not let Best Buy
All right. Well, that was kind of interesting. I mean, you stop and think. I mean, there's so many ways in which it can show up in everyday life. But of course, we don't see all of that. It's the engineers design everything, but behind the scenes, they're using a lot of trig functions. But the ones that might have surprised you were the music. Yes, there's a very close connection between math and sound. I mean, it's a very interesting area of study. And so, yes, we do see a lot of trig functions there because the sounds go through these cycles where they're repeated. So, there's a very close connection there. But obviously, anytime there's any kind of motion, especially when we're dealing with gravity, of course, a lot of, with NASA, they would have spent a lot of time using trig functions to help estimate, where to launch the rockets or the space shuttle and, how to get it back, of course. All right, well, anyway, now the next video that I want us to see is the introduction to chapter 11. It sort of lays the foundation for what's going to come afterwards. It's a very nice, quick look at probability theory. And it's kind of fun. I mean, it's not just, lecture about probability theory. It's kind of fun to watch too. And it starts to lay the foundation for everything that follows. And the concepts are not that difficult, but when they tie it all together very nicely, I think. So why don't we check this one out, and then we can start chapter 11. And maybe we can look at some more of these videos later on, maybe one more, and then we'll dive into the notes. So first, let me get this out to you. Basic probability, which I'm sure you'll like. It's a lot of fun, but also very interesting.
Teachers, I have a website that is going to blow your mind and help you and your kiddos out so much in the classroom. It is called Generation.
All right, let's check it out.
Science lessons, and they just launched their math series.
Hi, I'm Rom. Welcome to Math Antics. In this video, we're going to learn about how to do math with things that only sometimes happen. They might be likely or unlikely. We're going to learn about probability. Usually in math, we deal with things that always happen the same way. They're completely certain. Like if you add 1 and 1, you're always going to get 2. If you multiply 2 and 3, you're always going to get 6. There's no uncertainty at all. But in the real world, things aren't always so predictable. Take a coin toss, for example. We can't predict whether it'll be heads or tails. It's unpredictable or random. And that's why some people will flip a coin to help decide which of two things to do. That's how I make every decision in life. Why am I not surprised? Oh, no. Good luck. But even though we don't know what each coin flip is going to be, we do know a few things about it. We know that with a fair coin toss, that heads is just as likely to show up as tails. The probability of an event, like getting heads or getting tails, is a value that tells us how likely that event is to happen. With our coin toss, since each side is just as likely, and there's only 2 sides to a coin, if we flipped a coin a lot of times, we should expect that about half the flips will be heads and about half the flips will be tails. That means that the probability of flipping heads is the fraction 1/2, and the probability of flipping tails is also 1/2. Let's look at this in a little more detail on something called a probability line. It's a number line that goes from 0 to 1. A probability of 0 means that an event cannot happen. It's impossible. And a probability of 1 means that an event is definitely going to happen. It's certain. That's why the probability line only goes from 0 to 1. An event can't be less likely than impossible, and it can't be more likely than certain. A probability of 1/2, like with our coin toss, means that an event is just as likely to happen as it is to not happen. A probability less than 1/2 means that an event is unlikely, and a probability greater than 1/2 means that an event is likely. Oh, and in addition to fractions, it's also common to write probabilities as decimals or percentages, since you can easily convert between those three. A probability of 0 is the same as a 0% chance of something happening. A probability of 1/2 is the same as a 50% chance of something happening. And a probability of 1 is the same as a 100% chance of something happening. Now that you know how a coin toss works, let's see an example of an event that is unlikely. using something a little more complicated than a coin. Let's take a look at dice. A standard die has 6 sides numbered 1 through 6. When you roll it, any of those sides is just as likely to come up as the others. That sounds a lot like flipping a coin, doesn't it? Each side of a die is just as likely to come up as the others, and each side of a coin was just as likely to come up as the other. So you might expect that the probability of rolling a 3 is 50%. But remember, with a coin toss, there are only 2 possibilities, heads or tails. With dice, there are 6 possibilities. That's going to make a difference in its probability. One way to think about it is that it's certain that one of those 6 sides will land facing upwards, which is a probability of 1 or 100%. But since only one side can face upwards for a given roll, we have to divide up that value among all the possibilities. In the case of a coin toss, since there were only 2 possibilities, we had to divide the probability by 2. 1 divided by 2 is 1/2, which is the decimal 0.5 or 50%. But with the die, we need to divide the probability up evenly between 6 possibilities. 1 divided by 6 is 1/6, which is equivalent to 0.167 or 16.7%. That would be right here on our probability line. That means it isn't likely that I would roll a 3, for instance, but it's just as likely as rolling any other number. And since all 6 numbers have the same probability, each number should come up about as often as the others. To see if they do, I'm going to conduct some trials. That's an excellent argument. Allow me to deliberate. Guilty. Actually, when dealing with probability, a trial, which can also be called an experiment, is a process that has a random outcome, like tossing a coin, or rolling dice, or spinning a spinner. And the outcome of a trial is what happens in that particular trial, like flipping heads, or rolling a 3. So I'm going to conduct several trials by rolling a die multiple times and keeping track of how many times I roll each number. Aha! You said that each number was going to come up just as often as the other number. But look, there's more 2s than there are 5s. How do you explain that? Well, remember, we're dealing with things that are random. They're unpredictable. We can't know exactly what will happen, just what will happen on average. So now I have to calculate the average? Well, when we say on average, we mean that the more trials you do, the closer you get to the expected probabilities. Keep watching. There. Now that we've done a lot of trials, you can see that our totals are much closer to what you'd expect them to be. I guess you're probably right. That's one of the really important things to keep in mind about probability. If you do just a few trials, the results might not end up very close to what you'd expect. In fact, they could be way off. But if you do more trials, you increase your chances of reaching the expected probabilities. There's another thing I should point out. Remember, the probability of flipping heads is 1/2, and the probability of flipping tails is 1/2. The probability of rolling a 1 is 1/6, and the probability of rolling any other number on the die is 1/6. If you add up the probabilities for the coin flip, you get 2/2, or 1. And if you add up the probabilities for rolling a die, you get 6/6, which is also 1. And that's not just a coincidence. If you add up the probabilities of all possible outcomes of a trial, the total is going to be 1, or 100%, because it is certain that at least one of those possibilities will happen. Let's look at some more examples. For these examples, we'll use a spinner. If we had a spinner with just 6 equally sized sectors, the probabilities would be exactly the same as with dice. So we want a few more sectors. There, that's more like it. Now we have 16 equally sized sectors. So what's the probability of spinning a 12? Well, just like with dice, where we had to split up the 100% between all 6 possibilities, we'll do the same thing now, but we'll split it up between 16 possibilities. So the probability of spinning a 12 is 1/16, or about 6%, which is right here on the probability line. We can see that the probability of spinning a 12 is less likely than the probability of rolling a 3. That makes sense because there are more possible outcomes with our spinner. But what if we color some of the sectors a different color and we want to know the probability of spinning a certain color? Now we have 5 sectors colored blue and 11 sectors colored yellow. So what's the probability of spinning a blue? Remember how with the coin toss, we ended up with the fraction 1/2, And with the die roll, we got the fraction 1/6. In both cases, we had 1 as the numerator. And that's because we were interested in only one of the possible outcomes, like the probability of flipping heads or the probability of the number 3 being rolled. But in this case, the top number of our fraction will be 5 because any of these 5 sectors will give us the color we want. And the bottom number will still be the total number of possibilities, which is 16, because that's how many total sectors we have. So the probability of spinning a blue is 5/16, or about 31%. That's still considered unlikely, but it's more likely than spinning a specific number. And this method will work for figuring out the probability of any event. You just make a fraction with the numerator as the number of outcomes that satisfy your requirement, and the denominator as the total number of possible outcomes. Let's try the same method to find the probability of spinning the yellow. Our top number should be 11 because there's 11 yellow sectors, and our bottom number should still be 16. So the probability of spinning a yellow is 11/16, or about 69%. Now we finally have a probability that's considered likely. And it makes sense because you can see by looking at our spinner that it's more likely to spin a yellow than a blue. And you'll notice if we add up 5/16 and 11/16, we get 16/16, or a probability of 1. So that's a good sign that we did it right. Let's look at another example. Suppose we have a bag of marbles. There are 3 green marbles, 7 yellow marbles, and 1 white marble. If we mix them all up and pull out a marble at random, what's the probability of it being green? Well, the top number of our probability fraction will be 3 because there's 3 green marbles. So there's 3 outcomes that get us what we want. And the bottom number will be 11 because there's a total of 11 possible marbles that we can pull out. So the probability of pulling out a green marble is 3/11, or 0.27, or 27%. It's right here on the probability line. That means it's unlikely. And that makes sense because you can see that it would be less likely to pull out a green marble than one of the other ones. Let's try this again for calculating the probability of pulling out a yellow marble. This time, the numerator of our fraction will be 7 because there's 7 yellow marbles. The denominator will still be 11 because there's still 11 marbles total. So the probability of pulling out a yellow marble is 7/11, or 0.64, or 64%. Another example of an event that's likely. How about pulling out the white marble? Well, the top number will be 1, since there's only 1 white marble, and the bottom number is still 11. So the probability of pulling out a white marble is 1/11, or 0.09, or 9%. Not very likely. And if we add up these probabilities, we get 11/11, or 100%, just as we expected. All right, you should have a pretty good handle on basic probability now. You just have to remember to make a fraction with the numerator being the number of outcomes that give you what you want, and the denominator being the total number of possibilities. And we learned about the probability line, and that a probability can't be less than 0 or greater than 1, or 100%. We also learned that the more trials or experiments you conduct, the closer your results will get to the expected probabilities. Of course, the way to get good at it is to practice. So be sure to do a lot of problems on your own. As always, thanks for watching Mathantix, and I'll see you next time. And I sentence you to 5 years hard labor. Learn more at mathantix.com.
Amazon.
All right, then. I think you can see that that was the beginning of what we'll be looking at. And I think he really explained it very clearly, but it also was kind of fun to watch. You know, it's like having all those cool graphics is really very helpful in making this stuff more interesting. But it's going to, I mean, of course, a lot of what we'll be doing will be using that as a starting point and then building up to more complex ideas. But I think that's an excellent starting point for learning about probability theory. Now, the next video is really more for the fun of it than anything, but it's also brings us some very important ideas as well. And so we'll do this and then we'll get back into the notes. It's called How Many Ways Can You Arrange a Deck of Cards? And so I think you'll be surprised when you discover what the answer is. Okay, so let me just get this off to you and then we'll get back to the notes. Oh, hold on. Oh, wait. Oh, no. What am I doing? Hold on. All right, let's check it out.
Pick a card, any card. Actually, just pick up all of them and take a look. This standard 52 card deck has been used for centuries. Every day, thousands just like it are shuffled in casinos all over the world, the order rearranged each time. And yet, every time you pick up a well-shuffled deck like this one, you are almost certainly holding an arrangement of cards that has never before existed in all of history. How can this be? The answer lies in how many different arrangements of 52 cards, or any objects, are possible. Now, 52 may not seem like such a high number, but let's start with an even smaller one. Say we have 4 people trying to sit in 4 numbered chairs. How many ways can they be seated? To start off, any of the 4 people can sit in the first chair. Once this choice is made, only 3 people remain standing. After the second person sits down, only 2 people are left as candidates for the third chair. And after the third person is sat down, the last person standing has no choice but to sit in the fourth chair. If we manually write out all the possible arrangements or permutations, it turns out that there are 24 ways that 4 people can be seated into 4 chairs. But when dealing with larger numbers, this can take quite a while. So let's see if there's a quicker way. Going from the beginning again, you can see that each of the 4 initial choices for the first chair leads to 3 more possible choices for the second chair. And each of those choices leads to 2 more for the third chair. So instead of counting each final scenario individually, we can multiply the number of choices for each chair, 4 times 3 times 2 times 1, to achieve the same result of 24. An interesting pattern emerges. We start with the number of objects we're arranging, 4 in this case, and multiply it by consecutively smaller integers until we reach 1. This is an exciting discovery, so exciting that mathematicians have chosen to symbolize this kind of calculation, known as a factorial, with an exclamation mark. As a general rule, the factorial of any positive integer is calculated as the product of that same integer and all smaller integers down to 1. In our simple example, the number of ways 4 people can be arranged into chairs is written as 4 factorial, which equals 24. So let's go back to our deck. Just as there were 4 factorial ways of arranging 4 people, there are 52 factorial ways of arranging 52 cards. Fortunately, we don't have to calculate this by hand. Just enter the function into a calculator and it will show you that the number of possible arrangements is 8.07 times 10 to the 67th power, or roughly 8 followed by 67 zeros. Just how big is this number? Well, if a new permutation of 52 cards were written out every second, starting 13.8 billion years ago, when the Big Bang is thought to have occurred, the writing would still be continuing today and for millions of years to come. In fact, there are more possible ways to arrange this simple deck of cards than there are atoms on Earth. So the next time it's your turn to shuffle, take a moment to remember that you're holding something that may have never before existed and may never exist again.
Well, that was pretty interesting. Imagine that every time you shuffle the deck, you might be creating a new arrangement that has never been seen in history, the history of the universe. That's because the number of possibilities is so enormous that if somebody sat there and did this all the time, it would take centuries, I guess, to, well, let's say a long time to find every single one of them. So anyway, so let's get to the chapter 11 notes. And these, as you'll see, are pretty closely related to what we've just been doing. So we're not going to actually start with actually probability theory proper. We'll do that in a few minutes. First, we're going to start with something a little different called arithmetic and geometric sequences. Then we'll dive into what is properly probability theory and counting theory. So the sequences are an important idea, especially for computer applications. So you might remember from your travels that you were introduced to a very interesting idea called a Fibonacci sequence. All right, let's just see. If you haven't seen this before, I think you'll find this very interesting. If you have, you know what I'm talking about. It's a sequence is basically a set of numbers that are tied together by some kind of a pattern or a formula. So like, let's just say, start at the beginning. Let me just quickly step back here for a second. For example, an arithmetic sequence simply means you have a string of numbers like this, or a list of numbers that are listed in a particular order, and you should be able to tell from the pattern what comes next. So here, for example, it's pretty obvious that 7 comes next because this sequence is set up so that we start with 1, and then in order to get to the next term, we simply add 1. 1, 2, 3, 4, 5, 6, et cetera, et cetera. The 3 dots here, of course, means that this goes on forever. And there's a pattern to it. You could actually write a formula that tells us how to generate all of these different numbers. But like I said, the one that you may have run into before, the so-called Fibonacci sequence, is a little bit more complicated than that. So it starts out like this. So just based on what you see right there, what do you think comes next? All right, now it's kind of tricky. If you've seen it before, you'll know right away, but if you haven't, this one is a little bit tricky. But once you notice the pattern, you'll realize, oh, this isn't that difficult at all. Don't have any ideas of what number is next? Okay, here, I'll spoil the surprise by telling you it's 8. Now, why is it 8? Well, I'll tell you why. Because the way it's set up, the first 2 numbers, as you can see, add up to 2. The second and the third numbers add up to 3. The third and fourth numbers add up to 5. And the fourth and fifth numbers add up to 8. In other words, what happens is, except for the first 2, which are the starters for this sequence, after that, every one of these terms is the sum of the previous 2 terms. And so the next number would be 13, 21, 34. Yes, 34. Oh, no, not quite. 13 and 8 adds up to 21. And then we have 34. And then we have 43. Sorry, what am I saying? 43. 34, 55. That's better. And so this Fibonacci sequence is more than just of idle curiosity. There's a lot of interesting results that can be derived from it. So what I'm going to make a note to myself. I'm going to see if I can find at least one video that goes through this, because it's a very interesting idea. And some very surprising results have been derived from it throughout the centuries. This idea was thought of in, I believe, the 15th century. Let's just do a little research here. Fibonacci was a very famous mathematician in Renaissance Italy. And oh my God, it's even further back than that. All right. Oh, here we go. History. Here it is, 1202. Wow, it's even further back than I realized. 1202, he invented this. It is used to calculate the growth of rabbit populations, okay? He considers the growth of an idealized rabbit population, assuming that a newly born breeding pair of rabbits are put in a field. Each pair mates at 1 month, and at the end of the second month, they always produce another pair The rabbits never die, but they continue breeding forever. How many pairs will there be in 1 year? And so that's what he came up with. And you can see the numbers are going to get very big very, very quickly here. And then here's the mathematics behind it. And so, all right, so we'll get back into this later on, but I just wanted to introduce this to you because I thought you might have seen this before in high school. If not, that's okay. We'll get back to this and we'll get more deeply into it. But for now, we're going to start our discussion of sequences with the simplest ones. We're going to be looking at two basic types, arithmetic and geometric sequences. So the arithmetic sequences are very straightforward because all you're doing is starting with some value, and then you are adding a constant term or a constant amount to each term. Each of these numbers, by the way, is called a term. And the commas are there, of course, to separate them. But the idea here is that we should be able to figure out what's coming next just by seeing the pattern that's been established. And this is called a sequence. So let me show you a few other examples. The first one we've already seen. Now look at this one. This one is also an arithmetic sequence because if you notice, every time we move to the next term, we're adding 3 to it. Okay. And so the dots mean this just goes on forever, but obviously the next term would have been 17, and then 20, 23, 26, and it goes on and on forever. Up here, in each case, we're adding 1. If you also notice, we don't have to start with 1. We can literally start with any number we choose. But if you notice, though, we are restricted to integers. Sequences are normally defined on integers, although, you know, we'll just do that here. I guess that certain types of sequences are not integers, but the ones we're looking at here are going to be integers. This one's interesting because if you notice, it's actually going down, and that's because we're adding -1 to each term to get to the next term, which means we'll have 5, 4, 3, 2, 1, 0, -1, -2, et cetera, et cetera. So all of these are arithmetic sequences. The word arithmetic is meant to indicate that each term has a common difference. In other words, if you calculated the differences between consecutive terms, you'd always get the same number. So here, for example, 9 minus 10 is -1, 8 minus 9 is -1, 7 minus 8 is -1, and that'll go on forever. Now, you wouldn't think so, but these can be awfully useful in deriving results, especially when there are an infinite number of values involved. So what we want to do, though, is this. We know perfectly well what the pattern is. Suppose for some reason we needed to know the 100th term in the sequence. Well, we could certainly do that by writing them all down because we can see for ourselves how that works. And in fact, if we went to Excel, now if you don't have Excel, you should start learning it. Let's take this one and see what we can get. 2, 5, 8. Now, Excel is smart enough to say, if you start a pattern like this, you can just drag it and it will fill in the rest. Now watch this. You see how it goes to 11, 14, 17. It knows what it's doing. So if I need 100 terms, look how easy this is. I just drag it down to row 100. All right, not here. So the 100th term is actually 299. So you know what, that wasn't so hard, but what if I had to do that by hand? It could take a very long time. So it turns out that there's a formula we can use that will take care of this for us. So what is that formula? Well, let's find out, and then we'll confirm it on this case. So the formula we'll be using is this. Now, before we go any further, I just want to point out that for the terms in the sequence, let's say, once again, we're thinking about 2, 5, 8, et cetera, et cetera. Each term is referred to as A with a subscript that tells us which term it is. Okay, so that's the notation we'll be using. A1 means the first term, A2 is the second term, all the way up to wherever we go. So AN is, of course, then the nth term, the one we're looking for. And N is the term, same thing, term number of the term that we are looking for. And then D is the common difference between the terms. Okay, so we've got the starting term, we've got the number of terms, we've got the common difference. With all that information in place, we can figure out, in principle, any term that we choose. So let's just try that with the example we just did. So we'll say that for the sequence, two, 5, 8, 11, 14, etc. What is the 100th term? Okay, well, if that's the case, A1 is 2, N is 100, D is 3, because that's the common difference between all the terms. All right, let me just. There we go. All right, so what we're going to do is go get this formula again and make our substitutions. And then we're going to see that the correct answer is 299. That's which we already know because of Excel. All right, so AN equals 2 plus 100 minus 1 times the common difference of 3, 2 plus 99 times 3, 2 plus 297 equals 299. So there it is. We just confirmed that the 100th term does in fact have to be 299. So in principle, we can find any term in any arithmetic sequence we choose by using this relatively simple formula. Now, when you stop and think about it, the formula itself is not that terribly sophisticated. All you're doing is saying, listen, whatever the starting point is, the 100th term is 99 terms forward. So I'm just multiplying the 99 by the 3 common difference and adding them up to come up with my 299. So it's nothing terribly advanced, but it's important to understand how it works so you can see why this is happening. All right, now here's what we're going to do. Just to get some practice with this, we're going to say, all right, suppose you had this sequence. Now, first of all, you should ideally confirm that it is in fact an arithmetic sequence. Here you know that it's arithmetic because we have a common difference of 5. That's all it takes to be an arithmetic sequence. So that being the case, why don't we use this formula to figure out the 10th term of the sequence? So for this one, I'm going to leave it up to you to figure it out. All right, so why don't you take out your calculator and try it out and see what you get. And by the way, this one is only the 10th. If you really need to, you can write them all out just to double check your results. 100 is that's a long sequence. 10 is not such a big deal. So once you try the formula, and if you want to, you can double check by simply writing out the first 10 terms. Okay, 5 of them are already there, so they won't be that difficult. All right, let's see how you did. Well, first, if you write them all out, you'll see that the answer is 46. Well, that's the brute force approach, and that's fine when you only have 10, or if you have more, of course, you can use Excel, but why don't we use the formula? All right, well, first things first, the sequence started with 1, and then we're looking for the 10th term, so n is 10. 10 minus 1 is 9. The common difference is 5. So we do, in fact, end up with 46, as we saw on the previous slide. All right. Well, that wasn't so hard. So if that's the case, once we start getting good at this, let's try this one. Suppose here's another arithmetic sequence. And again, you can double check that by making sure that the terms have a common difference. In this case, that common difference is, of course, 4. So we're looking for the 9th term of the sequence. So again, if you want, you can feel free to write them out, but try the formula as well. All right, let's see how we did. So, oh, I guess I did not write them all out, but all right, let's do that just to start. So this is term 5, so we obviously are adding 4s. I think that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 34 is the correct answer, but let's see why. So the first term was 2. N is 9 this time. The common difference is 4. So you can see down here that translates into 2 plus 32, which is 34. Beautiful. So they're all exactly the same. Sometimes they're a little trickier because you may have a negative difference, for example. But basically, this is how arithmetic sequences work. Now, sometimes, though, this is not really what we're interested in. We may be more interested in adding up the terms of a sequence, or the first so many terms of a sequence. So here's a formula that we can use to do this. So, like, for example, if you had the one we had earlier, 2, 5, 8, 11, and 14. What if I wanted to know the sum of the first 5 terms? Well, certainly we can add them up. But you can see this is going to get very awkward very quickly if we have to add up more than a few terms. All right, we got 15, 26, 40. That's right, isn't it? Yeah. So instead, we have this formula. Now, if you notice within this formula, though, we do need to know the nth term. Okay, so we may have to use that formula from back here before we use the sum formula. Okay, so if, let's say, for example, you're being asked to calculate the first 100 terms, the sum of the first 100 terms, you need to know term 1 and 100. So you might have to calculate AN first before you apply this formula. And of course, S is meant to represent sum. Other than that, there's nothing new in this formula. Okay, so let's give it a shot. For example, what if we had the following sequence? Now, clearly it's arithmetic because, as you can clearly see, there's a common difference of 2 between the terms. We also know that A1 is 1. What we want to know is the sum of the first 5 terms. Okay, so A1 is 1. Now, because we already know the 5th term, we don't have to calculate it separately. A5 is 9, so this will be especially straightforward. So S5 would be 5, 5 is N, A1 is 1, A9 is 10. We divide that by 2. All right, so if you manually add these up, 1 plus 3 is 4, 9, 16, 25, yes. So if you add them up manually, you'll of course get 25, but thanks to our formula, we can see that this has to be correct. So now, again, if you have a small number of terms, you don't really need this formula. But if you have more than a few terms, obviously the formula starts to pay for itself. So, so you can see here that yes, in fact, we got the correct answer. So now what I'm going to do is copy this formula. And what I'd like you to do is come up with the sum of the first 6 terms. You can do it either way. You can add them up yourself. You can use the formula, but I think that at some point you'll want to start learning how to use this formula properly, because otherwise you'll run into a situation where you're being asked to calculate a large sum, and this helps reduce the risk of mistakes. All right, give it a shot. Okay, and also while we're at it, let's observe that A1 is 8 and A6 is 18. And N is of course 6. So if you took out a calculator and added these up, you'll get the right answer. Let's do that manually. 8 plus 10 plus 12 plus 14 plus 16 plus 18. That adds up to 78. Okay, so we already know that the sum is 78, but let's do the formula. Six, A1 is 8, A6 is 18 over 2. What do you know? It is in fact 78. That's what we figured. All right, well, that means we're in pretty good shape here. Okay. Now, by the way, there's a clever way of looking at this. If you want to think about it, let me just show you what this formula is really doing. Those are the elements. Now, what you're really doing is saying, all right, what's going on here? We have a pair of numbers whose sum is 26. We have another pair of numbers whose sum is 26, and another pair of numbers whose sum is 26. So between the 6 numbers, we have 3 pairs that add up to 26. So the total must be 3 times 26, which is 78. That's really what this thing is doing. I just thought you'd find that interesting. Very good. Now, the second type of sequence that we want to look at in this chapter is the so-called geometric sequences. So arithmetic are the ones where we have a common difference between the terms. Geometric are a little bit more complicated, not that much more. Instead of a common difference, we have a common ratio. So that means that we're multiplying the numbers instead of adding them. So for example, you might have something like this: 2, 6, 18, 54, 162, 486. What do you notice about these numbers? We do not have a common difference, but we have a common ratio of 3, because in order to get from one number to the next, you're multiplying by 3. And because we're multiplying instead of adding, this becomes a geometric sequence. And that's how you can tell them apart. Now, because these are different, of course, they're going to have their own unique set of formulas for finding individual terms and for finding the sums of terms. And they're a little bit messier, as you can imagine. So I'll tell you what, why don't we stop right here for our morning break. And when we get back, we'll dive into our geometric sequences. And when we're through with our sequences, we can then start probability theory proper. Okay, just like our videos, probability theory. And then we'll take it from there. Okay, so I'll see you all in a bit. And when we get back, again, we'll wrap up geometric sequences, and then we can start to actually explore probability theory. All right, see you in a while. All right, here we are again. So we're going to get back now to geometric sequences so you can see how they're defined. We have a common ratio between the terms so that, in other words, each one is being multiplied by the same common ratio to come to the next term. So here's some simple examples. And so you can see here, in this first case, clearly these numbers are all being doubled. So the common ratio is 2. In this case, each number is being tripled. And then finally, in this case, they're all being quintupled, which means they're all being multiplied by 5. And again, just like with the arithmetic sequences, they can start anywhere. Also, though, like the arithmetic sequences, we can actually have negatives. Okay, so let me show you a couple more interesting examples here. Let's say we had something like this going on. How about the sequence -3, 6, -12, 24, -48, et cetera, et cetera. Well, what's unusual about this one is that the common ratio is actually -2. You can tell because we're given the starting point, what we're actually doing here each time is multiplying by -2. And that's why the signs are alternating between positive and negative. All right, so we're multiplying it by -2 each time to get to the next term in the sequence. Now, here's something else that can happen. Let's say we have something like this. 5.5, 0.05, 0.005. What's going on here? The common ratio is 0.10 or 1/10. So yes, you can have a common ratio, which is a fraction, and you can have a common ratio, which is negative. So, and it can be both. All right, so the geometric sequences tend to be a little bit more involved than the arithmetic sequences. But luckily for us, there are formulas that we can use to identify any particular term in a geometric sequence and also define the sum of the first n terms. The formulas themselves are a little bit messier, but they're not that bad. So how do we find a specific term in a geometric sequence? Well, here's the formula, and you can see it's a little different than what we were using before. What's really important is that this R is the common ratio between the terms. The N is the number of terms that we're looking for. And of course, A1, as usual, is the first term. AN is the term that we're actually trying to find. So why don't we find an example? Now, in these cases, with the geometric sequences, it's even less, well, let's just say it makes less sense to try to do this manually than it does with arithmetic sequences, but you can still give it a shot. So here, for example, we're looking for the 7th term of the sequence. Now, clearly, in this case, the common ratio is 2. So if you want to write them out, that's fine, because you can see we've already got the first 5. The next one would be 32, and the next one would be 64, and you're actually done already. But why don't we fill these numbers into our formula? We're looking for the 7th term, so n is 7. We can see that A1 is 1. And then A7 is what we're looking for. And finally, the common ratio is 2. So if we plug in those numbers, A7 equals 1 times 2 with an exponent of 7 minus 1, or 2 to the 6th, which is 64, and we're all set. So there you go. So you can see it's not that difficult at all. All right. Now let's see. Let's try another one. So I'm going to copy this formula so you can see what we're doing. And what I'd like you to do is using both, you can multiply, but I'd like you to use the formula to figure out what is the fifth term of this sequence. Okay, just to get a little practice. Okay, so clearly this has a common ratio of 3, which means this term would have to be 243, but why don't we plug these numbers into the formula? So A5 is, now A1 is here. And then we have R, which is 3. The exponent is 5 minus 1. So 3 times 3 to the 4th, which is 3 to the 5th. And if you put that into your calculator, you'll see that this is indeed 243. Beautiful. All right. Let's see if there's any more of these. No, that's it. All right. Now we're going to move on to the sum formula, the sum of the first 5 n terms rather. The formula is a little bit messier than it was with the arithmetic sequence, but not that much messier. So let me show it to you really quickly. This is what it looks like. And so you can see all you need to know here is n, the nth term we're looking for. A1, of course, is the starting value, and R is the common ratio. So let's say this is our sequence. Actually, I'm going to copy this. And so first of all, let's confirm that this is a geometric sequence. And how do we know? Because I'm doubling. Every time I move on to the next term, I'm doubling, I'm multiplying by 2. So clearly, the common ratio is 2. The first value is 5. And so all we need to know is for S5, 5 times 1 minus 2 to the 5th power, all divided by 1 minus 2. We have to be a little careful with this one. 2 to the 5th is 32. So we've got 5 times minus 31 over minus 1. Now the negatives obviously cancel each other out. So you're going to wind up with positive 155. Now, if you take your calculator out and add those up, 5 plus 10 plus 20 plus 40 plus 80 is in fact 155. So either way, you will get the right answer. All right. So that wasn't so painful, but sometimes these numbers can get very complex. The actual logic isn't, well, it's not, let's just say that it can get very messy. All right, so that's pretty much our discussion for now of sequences. Now we're going to move into a slightly different area, which is the starting point for what we saw in our videos. In fact, especially the playing cards example, that video about playing cards ties in nicely to what we're about to do next. We're going to introduce something which is called the fundamental counting principle. And basically what this lets us do is figure out how many different ways a collection of objects can be arranged. Now, here the word arranged has a very specific meaning. So let's say, for example, you've got on your shelf, here's your shelf. Let's say you've got 2 trophies here. Let's say you were a good athlete in high school. This is your baseball trophy. And this is your football trophy. Now, this is a very simple example. You can put your trophies from left to right as baseball followed by football, or you can put football followed by baseball. Each of these is referred to as an arrangement because you're changing the sequence. There are 2 arrangements that we can create with these 2 trophies. And an arrangement simply means we're taking our objects and we are rearranging the order. Now, when it gets to more than 2, the number of possibilities grows very quickly, as you saw again in the video, where they were playing musical chairs, and you can see there were 4 people and we're trying to figure out how to seat them. So let's just say instead, let's imagine that it's 10 years from now and you're really doing well. You're one of the world's most famous mathematicians, and you bought yourself a house that has a 3-car garage, and you have 3 amazing cars to park in those 3 garages. So the question becomes, how many different ways can we park these cars from left to right? And each choice is known as an arrangement. So what we can do here is just start writing out all the possibilities. So using the abbreviations I for infinity, L for Lexus, and M for Mercedes, let's take a look at what's possible with 3 cars. Okay, and remember, each one of these is known as an arrangement. Okay, so I did this for you. I wrote them all out, and you can see all together there are 6 ways of parking our 3 cars. In each case, all 3 of them are parked. And the order is what's changing, the order of the letters. So each of these is an arrangement. Now, it turns out, of course, that doing this by hand is very awkward and it can take a very long time. So while it's nice that we can do this manually, it would be nicer if we could have a formula that would let us do this directly. And there does exist, it's not actually a formula, it's a mathematical operator. And what is this thing called? Let me show you. But before we do, let us think about this situation a little bit. For the first car, and they mentioned this in the video, there are 3 different ways of parking the first car. Once we've chosen the car for the first garage, there's 2 left for the second garage. And once we've chosen that car, there's only 1 left for the third car. So what's happening here is that you're multiplying 3 by 2 by 1, based on how many different ways there are to park the cars in each of these garages. So 3 times 2 times 1 is 6, and that's why we have 6 different ways of parking the cars. Because again, when you park that first car, any one of the 3 can go in the garage. There's 3 ways of doing this. For the second garage, one of them is already in the first garage, so there's only 2 left. And then finally, when you park the first 2 cars, there's only 1 way to park the third car. So altogether, there's 6 arrangements that we can create from these 3 cars. So the mathematical operator that we can use for this is very interesting. And oh, by the way, just out of curiosity, based on this logic, if I bought a fourth car and I built a fourth garage on my amazing house, how many different ways could I park the cars? Well, let's see. I've got it right here. Let's say we go out and buy a Rolls Royce. Now remember, we're doing very well these days. We're the most famous mathematician in the world. And for whatever reason, now mathematicians get paid lots of money, even more than, let's say, athletes. So here's your 4-car garage. And again, there's 4 ways of parking the first car, 3 ways of parking the second car, 2 ways of parking the third car, and 1 way of parking the fourth car. So all of a sudden, the number of choices goes up quite a bit. 4 times 3 times 2 times 1 is 24. So just by getting another car, all of a sudden, we went from 6 to 24 different possible arrangements that we could create with our cars. Now, the number will grow very, very quickly, as you can imagine. If we had 5 cars, then we're really talking about a lot of possibilities. So what we would like to do is introduce a mathematical formula that will enable us to do this directly. This is called factorial. This is a mathematical operator. N is some integer, which is not negative, by the way. This is pronounced factorial. So when you see something like this, you're supposed to pronounce it as n factorial. Now, this is actually on your calculators, no matter which one you have, including the iPhone calculator, it has it in there somewhere. Now, all the calculators don't implement it the same way, but they all have it. So here's how a factorial is actually defined. We start with 0 factorial. Now, this is only going to work with non-negative integers. In other words, if you try to type -1 factorial in your calculator, it'll give you an error message. If you try to type 0.5 factorial, it'll give you an error message. This only works for 0 and positive integers. The first 2 are just equal to 1. But once we get past that point, 2 equals 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. And you notice this is the number of ways of parking 3 cars. It's not a coincidence. And remember here, this is the number of ways from our earlier example of placing 2 trophies on a shelf. And then we saw when we got to 4 factorial, this is the number of ways of parking 4 cars. 4 times 3 times 2 times 1. Again, because you can park the first car 4 different ways, the second car 3 different ways, the third is 2, and then finally 1. So that would be the number of ways of parking 4 cars. And you can see the list goes on and on. For 5 cars, it would be 120. For 6 cars, it would be 720. That's a big number. I guess if you're LeBron James or somebody like that, you can figure this out just by buying the right house and then parking them. It would take a while, but eventually you'd figure it out. So yes, and it just goes on and on forever. And the numbers do get big in a real hurry. For example, let me show you in the next slide. 10 factorial is over 3 million. So if you had 10 cars, let's say you tell your chauffeur to figure out how many ways there are to park the cars, he'd be working at this for months. 3,628,800. So if you have this on your calculator, the key is most likely labeled x factorial. That's usually what happens. It's usually not n, it usually says x. Now, depending on the calculator you have, in some calculators, the 10 comes before the x factorial button. And in some cases, it's the other way around. So you have to experiment with your calculator. But with the iPhone, I'm going to try it right now. Oh yeah, with the iPhone, you're going to hit the number and then the x factorial button. which is in the extreme lower left-hand corner of the keyboard. Now, if you want to push your luck, let's try 30 factorial and look how big that number gets. In fact, it's so big that when you see it, you might say something went wrong with my calculator. But that E32 means this number is being multiplied by 10 to the 32nd power. Oh my God, that's a big number. That's probably the number of atoms in the entire universe. It's enormous. And based on the video we saw, how many ways are there to shuffle a deck? Now, with a deck of cards, you know, when you shuffle them, they're in a particular order. The first card is on top, the last card is in the bottom. And so that would be 52 factorial. So if you type that into your calculator, it's big, okay? I seem to remember him saying the exponent was 67. So let's try that, 52 factorial. Yeah, that's a biggie, 8.0658 E67 or 8.0658 times 10 to the 67th power. And so that's why in the entire history of the human race, we still haven't had time to find every possible arrangement of a deck of cards. So every time you shuffle the deck, you might be creating a completely new arrangement of the cards that has never happened before in history. It's kind of interesting to think about that. It's possible that this has never happened before. There's all kinds of, I mean, in probability theory, you can run across all kinds of weird results. Like I saw somewhere that somebody sat down and calculated that at any given time when you're breathing, there's something like a 20% chance that you're breathing in a molecule that was exhaled by Julius Caesar, something like that. You know, because you're constantly breathing and you're constantly bringing all these molecules into your system and you're constantly exhaling too. And so they bounce around and sooner or later they're going to get picked up by somebody else. So anyway, oh, here's a quick one. I threw this in there for the fun of it. There's a small museum that has enough wall space to hang 4 new paintings from left to right by a famous new artist. So this artist specializes in putting colored dots on white canvases. And they're all the rage. So they're very expensive right now. So how many ways can the museum hang those paintings from left to right? Well, we already know how to do this. We're not going to write them down. We're going to use the factorial operator. And that would be 4 factorial. Because we can hang the first painting 4 ways, the second painting 3 ways, the third painting 2 ways, and the last painting 1 way. So this matters a great deal. There was a scandal at one of the big New York museums where a very abstract painting was hanging on the wall somewhere. And it took about 6 months before the actual artist had time to show up and look at his painting in this museum. And it turned out all that time it was upside down and nobody even noticed. Now that's a strange painting. Nobody can tell if it's upside down or not. I'm not so sure that's a good thing, but it did actually happen. So the order, well, in that case, it was the way they hung it. Let's see if we can find the story. Oh, it was MoMA. Oh my God, 47 days. The Museum of Modern Art hung a Matisse upside down and nobody noticed. Ooh, well, you can see why. How would you know if this is right side up or not? 1961. The error wasn't discovered for 47 days. Among them was Matisse's son. He didn't know. But a Wall Street stockbroker was more observant. After 3 visits to the show, she became convinced that it had been flipped. She was certain he would never put the main, more complex motif on the bottom and the lesser motif on the top. And sure enough, Wow, look at that. Ah. Anyway, I thought you'd find that interesting. So in general, just as a general note, there are always going to be n factorial different ways to arrange n objects. Now, the next concept that we're going to be looking at involves something a little different. Rather than just arranging a group of objects, we're actually going to make selections from a group. Okay, so like imagine, you know that most museums have much bigger collections than they're able to show. Like for example, supposedly the Metropolitan Museum of Art in New York City, at any given time, they only have room for something like 1% of their collection. Let's see if we can find out. %. Okay. About 4% of their collection is on display at any given time. That's because they have so much art, and they must have enormous warehouses where they store it. So when you go in that building, I mean, it's a big building. They've got a lot of art out there, but you know, that's only 4% of their total holdings. That's pretty interesting. Now, but what that means though, is that they have to make a lot of decisions about what to show. Oh, what about the Louvre? I bet theirs is, oh my God, less than 1%, maybe even 0.1% of our collection. But of course, the Louvre is a lot older than the Met, but they can only show so much. So they have to make some decisions. So every time a selection of objects is chosen from a larger selection or collection, each selection that we can make is called a permutation if the order of selection does not matter. Okay, so what does that mean? Well, let's just say, I'm sorry, I said it backwards. The order does matter. In other words, in the order in which I select these objects makes a difference. So let me show you an example of this. Suppose that the students of SUNY Perch decide to start up a math club. I don't know, maybe there already is one. I'm not so sure about that, but let's say they decide to have a math club. There are 10 members, and we need to choose a president, a vice president, and a treasurer. Let's say that the school requires that to have a club. Well, nobody wants to volunteer. Everyone's like, no, I don't want to do it. Or I choose somebody else. So we've reached the point where we're desperate. So we're going to randomly choose names and assign them one of these jobs. So how are we going to do this? We're going to give everybody a number from 1 to 10, and we'll randomly pick 3 numbers. The first number that we pick is going to be the president. The second is going to be the vice president, and the third is the treasurer. So let's say that we pick the numbers 3, 1, and 7. So student 3, John Smith, is now the president. Student 1, Billy Robbins is the vice president, and student 7, Sharon Smith, is the treasurer. Now, suppose that we had picked the same 3 numbers, but not in that order. 731, does that matter? Yes, because now student 7, Sharon, is the president. Student 3, John Smith, what did I say? John Smith is the vice president, and then student 1, Billy, is the treasurer. So the order in which I select these numbers is is relevant, because the order in which I pick them determines the positions that these students will hold. So by picking 3 students out of 10, this is known as a permutation, because the order in which I selected the numbers does matter. Okay, so in other words, I'm picking our objects from a larger collection N in such a way that the order of the choices matters. When that happens, each choice is referred to as a permutation. You may have heard that word before, permutation, but this is what the precise definition. When I select objects from a larger collection in such a way that the order matters, each selection is called a permutation. So in other words, every time the Met chooses, let's say 10,000 paintings to put on display for that year, that is a permutation because the order, let's say that the order in which they select them also determines the order in which they hang the paintings. Then these are permutations. Okay, and that's the number of permutations they must have is probably astronomical. But anyway, let's do some simple examples here. Now, by the way, how many different choices are there? How many different ways can we fill these positions? Well, we could write down a list, but that would take a very long time because there's 10 students and we're picking 3. And each time we do this, we have to keep track of the order. So rather than doing that, we're going to introduce a new formula, and you'll see that it involves our old friend factorial. So the number of permutations that we can create is going to come from this formula. And if you notice, it's all in terms of factorials. N is the number of objects that we have to choose from, and R is the number that we actually choose. So this NPR is used to represent the number of possible permutations. Okay, so if you understand the factorial operator, this should not be difficult at all. So let's take this and apply it to our example with the 10 students and 3 officers for the math club. All right, so in that case, N is 10 because there's 10 students in the class, or the club rather, and R is the number of positions that we have to fill. So we're going to end up with 10 is N, R is 3. So when you plug everything in the denominator, you can see we have 10 minus 3. So we actually have the ratio of 10 factorial over 7 factorial, and that works out to be 720. So can you imagine if we decided to sit down and start writing them all out? That would have been a terrible mistake because there are 720 ways we can fill these positions, or we can think of this as 720 permutations. 720 different ways to fill those positions. That's a lot, isn't it? It sure is. All right, do we understand what a permutation is now? Remember, you're choosing objects from larger. With the arrangements, we were not choosing anything. We took all of the objects and just changed the sequence, like on the wall, for example, the paintings, how they hang. We used all 4 paintings, but we were just trying to figure out how many different ways there were to arrange them so that we could hang them up on the wall. Here, we're choosing some of the objects from a larger collection where the order does matter. All right, here's another example. Now, what if we're looking at horse racing? Now, with horse racing, typically there's the payoffs to the gamblers who are watching the horses are based on which horse finishes first, second, and third. Apparently, that's all that matters. The rest is irrelevant. All that matters is who finishes first, who finishes second, and who finishes third. So imagine you're going to the track and there's a race going on with 8 horses. And you're going to write down on your betting slip 3 numbers. For example, 1, 2, 3. That means you think that horse number 1 will win. Horse number 2 will come in second, and horse number 3 will finish third. And if you're right, you'll win a bundle of money. Okay. Now, clearly, if you write that down on your betting slip, it's a very different outcome than writing 2, 3, 1, because in that second case, you're saying, I think horse number 2 will win, horse number 3 will come in second, and horse number 1 will finish third. So that means each choice that you're making is a permutation because the order matters. Okay, the order of selection matters, and therefore, each choice that we can make or each bet that we can place is a permutation. So the question is, how many different bets can I place? I've got 8 horses and I'm picking 3 of them. So therefore, 8 is N and 3 is R. Okay, so I'm going to plug these into the permutation formula. And you'll see that I've got 8 factorial in the numerator, 8 minus 3 in the denominator, and the ratio of these two numbers. Oh, okay, wait a minute. Oh, okay, so 8 factorial is 40,320, 5 factorial is 120. Therefore, the ratio of these two is 40,320 over 120, and that turns out to be 336. So the 336 different bets that we can place on the horses when there's 8 of them and we have to pick 3. Beautiful. All right, so you can see the logic behind this, again, is how many ways can we choose objects in such a way that the order matters. So you're probably wondering, is there going to be a situation where the order of the selection does not matter? And the answer is yes. But before we introduce that, it just so happens that I have a cool video for you based on permutations. All right, so now that we understand what they are, why don't we take a look at this video? It'll be fun. Man, look at that Louvre. Can you imagine? The Louvre is an enormous building. I mean, it's like it covers a couple of football fields, and yet they still can only show 1% of their collection at most. Unbelievable. All right, so let's get this video going. Let's see. No, here it is. I've got so much stuff open. All right, let me get this.
Really, it helps you
Oops.
see math in a new way. From the Pythagorean.
Okay, here we go. All right, so here's the link. All right, let's check this out. It's a lot of fun.
Pythagorean theorem to the area of a circle.
Hi, and welcome to Kolu Math. Today we're going to be looking at permutations. Let's look at a quick textbook definition. An arrangement where order matters. Well, that's not particularly helpful. Your textbook might also have this. NPR equals N exclamation mark over N minus R exclamation mark. Not particularly helpful either. Well, let's take a look at an example and we'll see if that helps clear up some of this. Your town has a bike race every year, and this year you're going to be racing in it. But you're going to be borrowing your friend's bike, and he's left it chained up for you on a light post downtown. And you take a look at the lock and you realize you've forgotten what the combination was. So you take a look on the other side and it appears there's another lock. And you don't know what that combination is either. So, well, you need to get his bike out and we're going to have to, I guess, guess the combination. And the question would be, considering these two different locks, if we're going to have to guess the code, which lock would take less tries to go through all the possibilities? Which lock has the fewest possible permutations? Well, let's try to figure that out. Okay, so if we look at the first lock here, we know that there's 5 possible digits in the combination, right? There's 5 different wheels, and each of those wheels is numbered 1 through 8. Okay, so I guess what we could do is actually go over to the blackboard here and actually write out each of those possible permutations. We could do 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 3, 1, 1. Well, we could do that and go ahead through that process, and that would certainly work. But if we notice here, the blackboard is filling up, and we're still in the 1, 1, 4 range here. So we're going to have to find a quicker way to figure that out. But maybe if we hop over to the other lock, that'll be a little easier for us to figure out. Okay, so these are the old combination locks, and there's 3 numbers in each of these combinations, and each of those numbers could be between 0 and 39. So each of those has those options. So we could, all right, I guess back to the blackboard.
So if we take a look at the blackboard here, we could have a 0, 0, 0, a 0, 0, 1, a 0, 0, 2, a 0, 0, 3. And well, seems like there's a lot of them. More than I'm willing to write out. And let's face it, if this is ever going to be on a test, we're going to have to get to the end of the test before the bell rings. And I'll be writing this much information out, and I'm going to be in some trouble. So, well, let's take a look at the this lock here and see if we can make this question a little bit easier to figure out. Let's take out 3 of those wheels and look at a simpler lock here with only 2 possible digits. So we can get rid of that extra information there. So this one we could actually chart out on the blackboard. It wouldn't actually be too bad. So let's get started on that. 1, 1, 1, 2, 1, 3. And keep in mind that first number there is indicating the first number in the combination, and the second number there is the second number. So you can see we've listed out all the possible combinations there. If you notice we have, well, how many do we have? Let's see, if we have 8 columns and we have 8 rows, we can multiply those together, and that tells us we have 64 possible permutations. Oh, okay, that wasn't so bad. Of course, that was a lot easier than the problem we were looking at. But I wonder if we could take that same idea and extract it out to the bigger lock. So when we were looking at the smaller lock here and we've written them out on the board, we realized that we made columns and rows made of our different possible outcomes. So in fact, we had 8 columns and 8 rows. Maybe we could just multiply those values together to get 64 instead of having to write them all out. And we can actually use that same ideology on the tougher lock. So when we go back to having 5 possible digits, each with a wheel numbered 1 through 8, we know that we actually can look at the possible options for each of those possible digits. And we have 8 for each of those. We multiply those all together, 32,768 possible permutations. And we can apply the same thought process to the other lock. Here we had 3 numbers in the combination, and each number could be between 0 and 39. So if we look at the possibilities for each of those numbers, there are 40 possibilities. We multiply those 3 numbers together for the 3 different numbers in the combination, and that tells us we have 64,000 possible permutations. And if we compare the 2 together, we can see that the lock with the fewest possible permutations is the one on the left. And in fact, half of the possible permutations of the lock on the right. So if we guess with the lock on the left, we'll have far fewer guesses to make. And in fact, our friend is not so smart, and his combination was 1, 1, 1, 1, 1. So we guessed it on the first try. So we managed to make it to the race on time. And well, there you are back there in the race, all ready to go. And the prizes for the race are awarded for first, second, and third place. The question arises, how many different arrangements of first, second, and third place can be made from the racers in the race? Or how many permutations for the top 3 spots? Well, let's take a look. How many racers do we have here? 1, 2, 3. Well, let's just say 99. Let's just do 99 instead of counting there. So there are 99 racers total. And well, I guess we could probably put 99 into each spot there and multiply that. Probably makes sense. Wait a minute, does this make sense? Well, I don't know. We should probably take a look at it. So there's our 99 racers, and they're all at the finish line waiting for the prizes to be handed out. And there's only going to be a prize for first, second, and third. So the first person is announced, and that's our third place winner. So if you notice, we had 99 racers in contention for third place, but now one of them is already occupying third place. So we only have 98 racers in contention for second place. So one of those is selected because he got second place. And that only leaves us 97 racers to select from. So when we calculate our selections here, we can't just use 99 repeatedly because the situation changes. Somebody gets first place, well, there's only 98 racers looking for second. And if somebody gets second, well, then there's only 97 racers looking for third. So instead of 99 times 99 times 99, we're actually going to count down from 99. Because the first time there's 99 possible, somebody crosses the finish line, there's 98 people still on the race. Somebody crosses the finish line, there's still 97 people out there possible for third place. We multiply those together, and that gets us 941,094 different possible outcomes for first, second, or third. So let's look back at the textbook definitions here. And there's our NPR again. And the textbook tells us that's the number of permutations that can be made from n items when we select R. And there's that formula again. Now, what exactly is that exclamation mark? That exclamation mark is what we call a factorial. And a factorial is, so we have the number n there as a factorial. It's the product of all the integers. Remember, that's the whole numbers there that can be positive or negative from n down to 1. So let's look at an example here. Maybe this will help us take a look. So we've got a 5 factorial there. Remember, the factorial is the product of all the integers from n down to 1. So our first integer is going to be 5, and we're going to count down to 1. So 5, 4, 3, 2, 1, and we're going to multiply those because it's the product. And that's going to give us 120. Okay, so maybe this isn't so bad at all. And if we look at some of the first few factorials, you can see how the pattern goes. And that's the factorial. You start with the n value, you count down to 1, and you multiply all those numbers together. Okay, so just to make things easier here, why don't we just focus on these first 9 racers here so we can see these calculations at work. So if we had those 9 racers, we have 9 possible ones. First one crosses the finish line, there's 8 left. Second one crosses the finish line, there's 7 left. And we can multiply those values together to get a value of 504 different possible outcomes for first, second, or third when there's only 9 racers. You can see the drastic difference there between 9 and 99. So let's use the permutation formula here. NPR stands for the number of permutations that can be made from n items selecting R. Well, in this case, we had 9 racers and we were selecting the top 3. Okay, cool. So let's go ahead and plug it into that equation. That's not too hard. Let's do the parentheses first. 9 minus 3 is 6 on the bottom. So we have 9 factorial over 6 factorial, and we can plug those both into our calculator. That gives us 362,880 over 720. We divide that out. Sure enough, we get 504, just like we saw last time with our calculation. So we know we're doing the right thing. Take a look at this too. This is kind of interesting. If we actually expand these out in what we call a factorial expansion, so you can see all the numbers that multiply together, remember the rules of division, and we can actually cancel out the duplications we have here. So we can actually cancel out these numbers all the way from 1 to 6 on the top and bottom. And that leaves us with 9 times 8 times 7, which is the exact calculation we made the first time we set it up. Pretty neat, huh?
Wait a minute, sir.
Hey, Joe. How you doing?
Sir, could we try this with the previous lock question? Because I went ahead and calculated it, and 8 chose 2 is actually 56, which is not what we had before. So does this even work?
Really cool, Joe. You actually came across something there. It turns out that there are 2 different types of permutations. On the left here, we have the combination locks. And on the right, we have the race candidates, where several are selected there as winners and losers, quite frankly. So on the right-hand side, because we had that changing situation where people were selected, the selections depend on the other selections, okay? Think about that. If you get first place, you can't be chosen for second place. And if you get third place, well, you couldn't have been chosen for first place. So it depends who gets selected for which position. On the left-hand side, the combination locks, the selections do not depend on the other selections. You could have 5 twice in a row, or you could have 3, 4 times in a row. The selections do not depend on the others. And if you think about it like probability back in our previous videos, you can almost think of the events on the left here as independent and the ones on the right here as dependent. Because on the left, the selections are independent of one another. It doesn't matter, you can have the same selection 5 times. On the right-hand side, it's dependent. You can only be in one of the places at one at a time. Of course, don't use these terms around your teacher because she'll think you're crazy, because I've never seen anyone use these terms, but it's a pretty good way to separate them out. So those independent permutations on the left-hand side, they're the ones that do not depend on the other selection. Those are calculated with what we call the counting principle. And the counting principle is when you make spaces for each of the selections you make, and you fill them up with the number of possible selections for each of those and multiply them together. That's the counting principle, okay? Those dependent permutations you solve with the NPR, okay? So you use that equation and you plug them in. Actually, I'm gonna show you guys a little trick here for the NPR formula. Okay, if you remember when we calculated 9p3, and we crossed out the duplicates on the top and bottom of the fraction, that left us with 987. And actually, if you notice, that's only 3 numbers, the same 3 that's sitting next to our P there. So what we can do is actually come up with a little shortcut for calculating permutations that I used to teach my students that they really seem to like. Basically works like this. To calculate NPR, you make the number R into the number of spaces. So if you have 3 as the number for R, you make 3 spaces. If you have 10 for the number for R, you make 10 spaces. Multiply those all together. And then you're going to start with N in the first spot, and you're going to count down from N until you've filled up all the spots. Multiply those together, and you have your permutation, your number of permutations. Let's take a look at an example. So 7P3, we'd have 3 spaces because R is the number of spaces, and we'd start with 7 and count down for each one. So 7, 6, and 5, and multiply them together. If we had 6P4, we'd have 4 spaces because R is 4, and we'd start with 6 and count down and fill up the spaces and multiply them all together. If we had 8P7, we would have 7 spaces, and we'd start with 8, count down, and multiply those all together once we filled up the spaces. It's a nice kind of simple way to do permutations that maybe you haven't seen before. Next time, we'll be looking at combinations, and it's going to be pretty simple after all this. Okay, so see you guys next time.
Amazon employees earn at least
All right, so now we're going to show you the next one, which is the case where the order does not matter. And these have a different name, of course. These are known as combinations. So basically what's happening is you're choosing objects from a collection in such a way where the order does not matter. Like, for example, suppose that you have a coupon which entitles you to choose 2 free sodas at a supermarket. The order in which you choose, and let's just say that they have 10 available. The order in which you choose your sodas does not matter. Therefore, each choice is a combination. Okay, it has no bearing. I mean, if you pick a Pepsi and a Coke, it doesn't matter if you pick the Coke first and then the Pepsi or vice versa. The order has no bearing on anything. So in this case, these are called combinations. So now, of course, that's going to affect the formula for calculating how many different combinations we can create. Or here's another quick example. You're picking out 4 colors to paint your house with. Again, the order in which you pick your colors doesn't make any difference. So with 4 colors, it turns out that you can choose, I wrote them all down here, 6. Okay, so I basically just listed them all, but if you notice, this is the key detail. If these had been permutations, green followed by white would be a different selection than white followed by green. But here that's not the case. Same thing with green and blue, green and yellow, and all the rest. If these had been permutations, I would have to list all of these separately. And I'd have twice as many choices as in this case, where they're combinations, where the order of selection does not make any difference. So the question becomes, what does that do to our formula? All right, so I've repeated in the next slide the formula for permutations so you can see how it compares with combinations. So, well, you can see for yourselves, in the bottom I have the permutation formula. The combination formula has an extra term in there. We're dividing out by r factorial. What that is doing is eliminating all the cases where we have the same objects but in a different order. So the number of combinations will always be smaller than the number of permutations. So the formula is only slightly messier, but I mean, it is a little messier, but not much. the key to the whole thing here is making sure you know when to use each formula. That's really the big challenge, making sure you understand when we're dealing with permutations and when we're dealing with combinations. And of course, also when we're dealing with arrangements, that's a possibility too. So here we have an example. This is the one with the colors. When we have 4 colors to choose from, and we're going to pick 2 of them, where the order does not matter, N is 4 for 4 colors, R is 2 for 2 choices. And if you plug those in, you'll see that just like we did when we wrote out all the possibilities, you will in fact end up with 6. Okay. And also, had we done permutations, it would have been 12 because you would have had NPR. So 4 factorial is 24, 2 is 2. And yes, so if the order had mattered, then we would have had 12 choices. But when the order does not matter, we have 6. All right. So that's the only difference between the two. Now here's an interesting application of this. And this ties again back to that example we had in the video with the cards, except this time we're not just shuffling the entire deck. We're actually going to assume that we're playing a game of draw poker. Now, the way that works is that you've got the whole deck, 52 cards, and each person gets 5 cards in their hand. Now, when you pick up your hand, the order of the in which the cards are dealt to you does not affect the value of your hand. So what that means then is that each hand is a combination because you're choosing 5 cards from a deck of 52. The order, again, does not matter. So therefore, if we want to know how many different hands are possible with a standard deck of cards, we can plug them into this formula with N is 52 for the entire deck and R is 5 for the size of a single hand. Now, you may be surprised when you work through this to see that it's a very large number, maybe larger than you anticipated. So let's take a look at this. When you plug in the numbers, ultimately, you can reduce this to 52 factorial over 47 factorial times 5 factorial. And that gives us a number of just under 2.6 million hands. That's a lot of hands. Okay. So anyway, that's how combinations work compared to permutations. Now, I've got more videos, but I think right now, I think we can knock it off right here. When this is done, then we're going to dive into probability theory and see how that works. In other words, we're going to set up a framework for calculating the probabilities of events like we did in the first video, where they were trying to figure out how many, let's say the probability of picking a white marble out of the bag or getting, 2 3s in a row with the dice or whatever the case may be. We were going to set up a framework that makes it possible to calculate probabilities for just about any event that you could imagine. Okay, so we'll save that for next time. So we're still only part of the way through chapter 11 here, so we'll carry on with this. And next week, I mean, and then in the meantime, since we're not done with this chapter, I guess there's no problem sets that you can work on. So, just make sure you understand what we've been doing today. And also take a look at the solutions for the chapter 5 problem set to make sure you understand how those were obtained as well. So between now and next week, all you have to do is just make sure you understand what we've been doing. And so we'll pick it up here next Wednesday. And so unless there's any last minute questions, I will see you all next Wednesday, which will be November 10th. All right. Okay, you're welcome. See you all next time. I hope you had fun. There's some interesting stuff we did today, that's for sure.
Excuse me, Professor.
Yes.
Can I ask you a quick question?
Yes, go ahead.
My question is to review, or not to review, to look into this course this course is like, our grades.
Mhm.
I tried looking on Moodle and I had an issue. Like I couldn't like compared to this course, like this class and to my other classes, I'm able to see like, the grades for like the total average, I guess. And this one, it does for some reason on Moodle, it doesn't show. And I wanted to ask,
All
is
right.
there a way to access that or?
I'll tell you what, I'll look into that. It's possible they've done something incorrectly, so I'll let you know what happens with that.
Oh, all right.
Right, yeah, because I'm not a technology guy, and so if I've not done something right, I'll look into that and let you know what I discover. Okay,
All right, I appreciate that. Thank you.
sure, okay,
All right, have a good week.
all right, you too.
Take care, bro.
All right, bye.